In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the waters. And God said, "Let there be light." And there was light.
And then we were looking at Genesis 1:1. In the beginning, God created the heavens and the earth. We talked about that last week, and how the idea of heavens conveys the idea of space. Space was created in the beginning. And of course, there's two ways of looking at that first verse, and that verse has been dissected and reviewed and interpreted in many different ways. Where some people, the idea that, well, that's the kind of an overview of what God did, and then what follows after that is the more detailed. That's one way of looking at Genesis 1:1. Of course, our gap theorist would say that Genesis 1:1 took billions and billions of years, and then what happened after that took a little bit shorter period of time. And then there's even other theories about it. About Genesis 1:1, everything was built and it took billions and billions of years to build it. And then what is discussed thereafter is really talking about the Garden of Eden. That's kind of an unusual theory. We'll look at that in a few weeks when we look at the different cosmologies that are out there. Because I think it merits studying them to see what other people are saying. Not that we have all the answers to some of the dilemmas that we have when looking at the first part of creation, because there's quite frankly just a whole lot we don't know and we'll never know this side of eternity. But we're looking at what happened in that first verse and the things that were created in that first verse to try to fit what happens thereafter and come up with some rational idea of an explanation of what occurs in the first verse. But to me, clearly the first verse implies that space was created when the heavens were created, because we know that's not speaking about the stars or the moon or any of the galaxies or that sort of thing, because those things weren't created till verse 4. So when it says heaven, you either have to think, well, okay, that's the first verse is talking globally, and then everything after is more detail, or it's creating something other than just stars and galaxies. And I choose that it's creating space. I think that's what makes sense. So what happens about the earth? It says the heavens and the earth were created. Well, we know the earth wasn't completed on that first day, or at least not in the first part of the first day, because it was formless and void. And we'll look at that later on today, what that actually means. So the idea of earth could easily mean the idea of matter. Matter was created on the first day, and of course matter had to be created at some point. When we talk about matter, we're talking about particles, things that would come together to eventually form atoms, which eventually would form molecules, which would eventually form everything we need for life. And that's what happened on the first day. Also, in my opinion, what happened on the first day is all the laws that we have in place were created on the first day. The laws that we work under today, the constants and the laws that we seem to work under today, that we've come to understand over the course of man's lifetime on Earth. And what seems to work today is general relativity and quantum mechanics. And again, I'm not here to make physicists out of all of us, because I don't understand most of these things myself and probably never will. But I can just say that scientists have determined that that's the way the world seems to work. Relativity and quantum mechanics. And these laws may be modified at some time in the future, but at least to this point in man's history, that's what we seem to operate under. And we talked about special relativity, and relativity is, sounds like a big word and can't understand it, but all special relativity says is just that the laws are the same for all observers in uniform motion. And that's what allows you to be able to eat a sandwich on a plane going 500 miles an hour, if it's in uniform motion. Otherwise, if you didn't have the law of relativity, you could not do that. But it is a law and has interesting implications. And one of the interesting implications is that time is not absolute. We think of 20 seconds as 20 seconds. 20 seconds on Earth, 20 seconds on Mars, 20 seconds out in the universe. Is that an absolute number? Well, it's not. And if you think it is, it's just not. It's been shown that it's not. So we get all caught up on absolute time. 24 hours is literally 24 hours, but it is literally 24 hours. But it's not 24 hours throughout the universe. I'm going to show that in a minute. And this slide even points out to it. When you're moving faster, time dilates. And when you get close to the speed of light, it dilates almost in numbers that are hard to conceive. Now we can't travel at the speed of light. Never probably will be able to. But we have jets that go pretty fast, and they have proven this through atomic clocks, that as you're traveling faster, time seems to dilate. It also changes depending on where you are as far as altitude is concerned. And we talk again, this slide, we talked about this a little bit last week, so I don't want to go into it. But one thing I think is an interesting implication of this, and I just find it interesting, I don't know how it applies necessarily to what we're studying per se in the first verse, but with this time dilation, you understand that if you could send someone into outer space going close to the speed of light and dilation would occur, then it has very interesting implications. And Stephen Hawking has talked about this, and he's done the math, and he has calculated that it would take 6 years at full power just to reach these speeds, getting close to the speed of light, like 94 to 95% the speed of light. But after the first 2 years, it would reach half the speed and would be far outside the solar system. In another 2 years, it would travel at 90% the speed of light. And he's calculated, I don't think I have that on there, but it's calculated that when you get close to the speed of light, the person traveling close to the speed of light, one day would equal 360 days on Earth. Okay, so when you get close to the speed of light, is that what it says? First paragraph. Yeah, a day on the spaceship traveling speed of light would be equivalent to a year on Earth. The first sentence there. So what does that mean? That means if we ever were to send someone to outer space, let's say he went, the sun's only what, 8 seconds away. It's not a light year away. You can get to the sun, it takes 8 seconds, I believe, for the light of the sun to get to the Earth. So that's not very far. But let's say you were traveling to a star that was a light year away. Well, what's a light year? A light year is the time it takes for the light of a sun to get here. And 1 light year means it would take 1 year for that light to get here. The sun takes 8 seconds, so it's nowhere near a light year away. But let's say we were able to reach these speeds that Hawking's talking about. And he says it's theoretically possible to get close to the speed of light. You can't ever get the speed of light. Nothing travels faster than the speed of light, according to relativity theory at least. But if you got close to it, and let's say you went to a star that was a light year away and returned. So you got there in 1 light year and you returned in another light year. What would you find when you got to Earth? You would find, and you would be 2 years, you would have aged 2 years during that time. But what you'd find on Earth is that the Earth would be 750 years. So you wouldn't know the people here when they got here, and they wouldn't know you except from a historical point of view. And you say, well, that's impossible. That cannot happen. But it is very theoretically possible for that to happen. And so it's just sort of an interesting thing. It sounds science fiction. Now, you can't travel back into the past, but you can travel into the future, if you will, because when they get back, they would have aged 2 years if they were going one light year per year, and it taken them a year to get there because it takes a year for that light to get here. And if you're close to the speed of light, it would therefore take you about a year to get to that star. But when you got back, none of your relatives would be here. In fact, the Earth would have aged 700 years, and you would have aged 2. And that's just the implications of relativity theory, and it seems to be true. Again, I don't know what we do with that in this class, but as a result of that, and one might think that this time dilation is about clocks. No, it's not about clocks. It's about time. And so as a result of that, creationists, some very bright, intelligent creationists that are physicists and astrophysicists, have tried to solve the dilemma of the light year phenomenon that we see. Because one of those dilemmas is, how can the Earth be 6,000, 10,000, whatever years you want to use, and yet we're seeing stars that are 3, 4, 10, 100 light years away? That doesn't jive, does it? If it takes that long, then the Earth can't possibly be that old. Well, understanding the effects of gravity, proven using atomic clocks, and then assuming the Earth represents the center of the universe, Russell Humphreys, PhD in physics, has calculated what he calls a white hole cosmology that solves the problem of time travel. Okay? Now, I'm not going to be able to tell you in detail what white hole cosmology is. I'm not smart enough to do that. Dr. Humphreys is a very brilliant man, He's been criticized, as you can imagine, by the naturalist for this theory and how this theory doesn't make sense and his mathematics is all wrong. Of course they're going to criticize him. They say he makes assumptions and things that are not observable. Well, guess what? They make assumptions of things that are not observable as well. So they want to have it both ways. They can make those assumptions, and since everybody else doesn't agree with him, he has to be wrong, right? But he's used a white hole cosmology. You know what a black hole is? Anybody know what a black hole is? You've heard the word black hole. Black hole is an area of space, and they've never seen a black hole. You can't see a black hole. It's a black hole. How would you be able to see it? It's black. There are evidences that they're out there. That's been shown, but you can't actually see one. But in a black hole, gravity is so intense that light cannot escape from it. That's what a black hole is, and that's why you don't see it. Light cannot escape. And if you got to what's called the event horizon of a black hole, you would be sucked into a black hole and you'd never get out. Well, you'd be destroyed when you got sucked in anyway, so it's irrelevant. You wouldn't be able to get out. Nothing escapes a black hole. White holes are the opposite of black holes, if you will, where things can escape and you don't fall in a black hole. And white holes are also theoretical. They haven't observed white holes as well, but it fits within the realm of relativity. Even the naturalists will say that. They won't deny that there's white holes. So Dr. Humphreys, his opinion is basically that the Earth was created in a black hole. And that's, and because of that, the appearance of time, billions and billions of years, could be there, and yet it only takes 6 days to create the Earth. Now that's his theory. And again, I'm not going to go into great detail with it because I don't know it that well. But he's highly criticized for that. But he's an astrophysicist. He's not a creationist that just on the top of his head came up with that. He's done the studies, and he has to make an assumption for that. And for this to occur, according to Dr. Humphreys and even the naturalist, for that to occur, the Earth had to be the starting point for the universe. The naturalist would say there is no starting point. I don't understand that. Seems like to me if you have a big bang, the bang had to start somewhere. And where that bang started would be the center of the universe. So even if you believe in the Big Bang Theory, to me you have to have a starting spot, a starting point. So for this to work, the Earth has to have had to be the center of where the universe began. I don't have any problem with that, especially from the first verse of Genesis. And there's no way to disprove or not prove it, but that's an assumption you have to make for white hole cosmology to occur. But it is an attempt to explain that phenomena of how stars and galaxies can be light years away and yet the Earth only be 6 days. It's a matter of time, and the concept of time dilation fits into the concept of white hole cosmology. Now I would entertain questions, but I probably wouldn't know how to answer them. So you can ask me later, but it is an attempt, and it sort of makes sense to me when you understand the concept of time, and that time is not absolute. And I think that's what gets us into trouble sometimes, is because we're trying to make time an absolute phenomena, and it just isn't. God has no time. God transcends time. There's no such thing of time before time was invented. That sounds crazy, but it does. So this does violate the current assumption of the cosmologic principle, or the Copernican principle, which states that the universe has no starting point and no boundary. I'm talking about the white hole cosmology. Now there's another dilemma too. We're not going to deal with it in this class so much, at least right now. And that is when we look at cosmic background radiation. Now I know that gets a little deep as well, but cosmic background radiation is radiation we're receiving on a daily basis from outer space, and that cosmic background radiation seems to be millions, if not billions of years old. And again, we'll talk about that a little bit more when we look at some of the other cosmologies out there. But the chance that the Earth would be the center of this is exceedingly improbable in likelihood, but would in fact make the Earth a very special place indeed. So if that's the case, if the Earth was the starting point for the universe, then that would have serious implications as well, meaning the Earth would be a very special place. Well, we're going to look at that in some detail, because the Earth does appear to have a very special place in the universe. And you got a glimpse of that in a tape that you saw a few weeks ago when I was out of town. That's what that's all about. And so that would even smack a purpose, wouldn't it? If the earth was the center or the starting point for the universe, that would smack it as a purpose. And of course, this is rejected by most theorists. But in fact, the earth the earth does seem to be very special and designed for life. And according to Dr. Ross, as I said last week, is a progressive creationist. I don't agree with everything he says, but what I do agree with is that there does seem a very special place in the universe for Earth and the universe itself, and it had to be fine-tuned to 10th to the 37th power. That's a large, large number. Let's look real quickly at the laws that were put in place at the very beginning by God, and that man has discovered over the years of time. And general relativity is the first one. Albert Einstein, everybody knows Albert Einstein, discovered this and published a paper way back in 1916, which revolutionized physics and science at the time. And he was able to show that the alteration of space is like a curvature. So we would say that matter or energy bends space. And gravity, therefore, then his general theory of relativity, talk about his special theory of relativity. But the general theory of relativity is this, and that is gravity. Now, man has always been trying to understand, why do we have gravity? Well, God just put it there. Well, that's fine. God just put it there. But see, God gave us minds to think so we can try to figure out why we actually have it. Because our bodies work in a certain way. We spent a lot of time last time looking at that, and we've come up with how our bodies work. Well, physicists come up with how the universe works. And there's nothing wrong with looking at these things, in my opinion. And certainly Einstein was a brilliant man. Don't know when we would have come up with some of these theories, if ever, if not for him. But the idea of gravity is it's a bending of the space-time continuum. That's what it seems to be. And that's what he says. Gravity, therefore, is the bending of the space-time continuum. And evidence for this was first demonstrated by Sir Arthur Eddington in the eclipse of the sun that occurred. And what actually Eddington did really had to do with light. That's what he really did. But it had to do with general relativity as well. We think of light as having no mass, and we're going to study light very shortly. Not today, the next week, and what the aspects of light are, because we know light was created too, wasn't it? Therefore, God said, let there be light. And so we're going to look at that in the second verse of Genesis. So light had a beginning as well, but we think of light as having no mass, that it's just, well, light is light. Well, there's properties of light that are interesting, and one is that light does seem to have mass. Okay? And so what Eddington did was he looked at the eclipse of the sun. He had to wait to 1919. There was an eclipse of the sun that occurred like in 1914 or 15, but there was a little problem that was going on in 1914 and 15, and that was World War I. And so he wasn't able to do his studies then, because it wouldn't be it'd have to be after 1960, but it could have had occurred in 1916. So he could have done this study earlier, but because of World War I, he had to put it off. And so what he's able to see is when there is a total eclipse of the sun, then light is going around the moon, okay? And he was able to see the light and able to show that light was actually bent. And the only way it could be bent was by the gravitational force of the moon and the earth. And so he's able to show that's been repeated several times now. So general relativity predicts, as a result of that phenomenon, that the universe is expanding. And Edward Hubble showed that in 1928. And he looked at Doppler studies to show that, red and green, a chemical that's a certain color shows that it's going away from us. And that's what Edward Hubble showed, and that's agreed by all physicists, that the earth is expanding. And that's what the Bible says, and that's consistent with Psalms 104, verse 2. Now, this figure on the right is not a biblical figure. That's a figure, though, of the Big Bang there on the right. But same idea, though, the stretching out of the heavens like a curtain. And so the earth is expanding. No, not the earth. The universe is expanding. And as I said last week, that sort of has spiritual connotations as well. Because if something is expanding, what does that imply? It had a beginning. Okay? And it's interesting, when I was reading Stephen Hawking's a little bit and on this time dilation, and he was talking about Stephen Hawking saying you can travel into the future by getting close to the speed of light, but you can't travel in the past. No matter what Back to the Future movies show, you can't do that. And he says the reason you can't do that is because it violates the cause and effect principle. Duh. You know, cause and effect. He admits that there's a principle called cause and effect. So we looked at this last week as well. If there's a universe, doesn't that imply a cause? So there's a cause and effect except for everything but the Big Bang for our physicists, which violates even what they say. But the universe is expanding, and it appears to be expanding, and I believe that all began in the first chapter of Genesis. Now, the other universal mechanism instituted at creation would appear to be quantum mechanics. And quantum mechanics came up very close to the same time of Einstein, and Einstein knew about quantum mechanics and quantum physics, but he died before a lot of the principles were pretty much proven in quantum mechanics, and he did not agree with the uncertainty principle, which is part of quantum mechanics. But relativity does a very, very good job explaining large objects, the universe, the galaxies, even things that we see around us all the time. But what relativity does not do a good job of explaining is things that occur at a subparticle level, or at the particle level, or the subatomic level. Quantum mechanics had to be invented to describe those things, because relativity and gravity could not explain them. What I mean by that is, and again, I don't know the mathematics, couldn't begin to do the mathematics for these sorts of things, but from what I understand, the mathematics for relativity does not work when you get into the subatomic level. They just don't work. When you start using those mathematics, they don't work. Corollary to that, the mathematics that we see in the quantum level, at the subatomic level, don't work when you look at relativity. So there's two major theories that are going on in our universe today that we understand, and that is quantum mechanics. And we're not going to spend a lot of time on that, but it involves something called the uncertainty principle, and that was a fellow by the name of Heisenberg that came up with the uncertainty principle. Heisenberg's uncertainty principle says that you cannot measure velocity and the location of a particle at the same time. Just the observing of that would change what you're trying to find. So you can never know absolute certainty of where a particle is or the speed of that particle at the same time. That may sound irrelevant to you, but it actually has a whole lot of relevancy. And so quantum mechanics really deals in the laws of probability because of this uncertainty principle. So you can figure out something that is very, 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 very probable, but you can never say it absolute. So this results in all kinds of weird ideas. I mentioned one a few weeks ago in our evolutionary class about Schrodinger's cat. You remember that? We talked about the cat in the box that had the cyanide pellet. That's kind of a theoretical offshoot of the uncertainty principle. The other offshoot of the uncertainty principle is if I threw a tennis ball at that wall and I threw it enough times that eventually that tennis ball would go through the wall. I don't mean make a hole in the wall. I mean it would go through the wall. Now these are theoretical. I mean, nobody's observed any of these things, and some of this is crazy, and there's obviously no proof of that, but it does go down to the uncertainty principle. That's the equation for the uncertainty principle. But again, it's just the act of observing something changes what you're trying to find, and you can't ever know the location or the speed of a particle at the same time. That is a part of quantum mechanics. You say, is that relevant to our society? Well, it is. Because if you didn't have quantum mechanics, your cell phones wouldn't be working. The quantum mechanics is responsible for the technology that we're experiencing today. And I could go on and on with the things it's responsible for. How? I don't know. I just know that's true. Without understanding quantum mechanics, we could never come up with the cloud. You know, this concept of the cloud. Could not come up with a concept of how your cell phone works and other computers work and so forth. All of that is a direct result of these brilliant men coming up with quantum mechanics. So our world does seem to work that way. Now, this is another picture of Schrodinger. And quantum mechanics implies that the universe is not necessarily deterministic and posits a wave-particle duality of electrons and indeed matter, and that's true. When you look at an electron is a particle, but it's also a wave. And if you look at experiments and you try to show that an electron is a particle, you'll find that it's a particle. If you do experiments that try to show that an electron is a wave, you'll find that it's a wave, okay? Interesting phenomenon, but it's true. That's the way electrons work. And so it's sort of this duality of electrons, and indeed light's the same way as well. We look at light, I just mentioned, light seems to be a wave. We talk about light waves, don't we? Ultraviolet light waves, infrared light waves. But yet, light waves have photons, and photons imply mass. So some people don't like the way quantum mechanics feels. In fact, the famous quote by Albert Einstein about this uncertainty principle is he didn't believe it because God doesn't play with dice. That's a famous quote of Albert Einstein. Now, I think he later regretted that statement, but it didn't feel right. But once again, it's responsible for the technology advances that have occurred in the last 5 years, the major advances that have occurred in the last 50 years, excuse me. Now, as a result of this physical phenomenon of physics, some have tried to expand both relativity and quantum mechanics to a philosophical point of view. In other words, some have argued that quantum theory and relativity violate biblical principles. The Copenhagen interpretation put forth by Danish physicist Niels Bohr attempted to bring philosophical ideas into quantum theory to bring physical ideas of quantum theory into a more philosophical realm. In other words, if there's an uncertainty principle, then there's an uncertainty, for example, if there's a God or not. That's kind of a big picture of that. Well, the problem is that's not what quantum physics is trying to prove or even states. That becomes a lot more philosophical. Non-determinationalism of the uncertain principles lead some to believe that reality was even in question. But that's taking that theory too far. Now, I've already mentioned what Einstein said there. So this is sometimes called the Copenhagen interpretation, and it's a perversion of quantum theory, in my opinion, and in a lot of people's as well. And relativity. Some have argued that relativity is equated to moral relativism. That's not relativity. That's philosophy. You understand? So to say that relativity equals moral relativism, in other words, sort of the ends justifies the means idea, everything is relative, but that's not relativity. That's a perversion as well. Well, what about string theory? And then we'll end this discussion and go to the second verse. What's string theory? String theory is an attempt to explain everything. I just mentioned that relativity and quantum mechanics don't jive mathematically. So since those two phenomena have been observed, there's been an attempt by physicists to join them together in one global unifying theory. That's what Einstein was looking for, a unifying theory, because again, we have relativity that explains large objects. You have quantum theory that explains little tiny objects, but they don't jive with each other, hence they come up with string theory. So, you've heard of string theory? I think most people have, but I've read a book on it and still don't understand what they're trying to say. So it's not easy, but it's very difficult. But in string theory, all matter consists of very tiny strings that vibrate at different frequencies, not just particles. And to be valid, an additional 6 dimensions have to be there that we can't see in our world. These are dimensions we can't see. So these dimensions have to be tightly curled up in the particles themselves in order to exist. Problem with that, string theory cannot be documented because extremely high energies would be required to accelerate particles to expose the 6 dimensions, and such particle accelerators simply don't exist at our time. You've heard of particle accelerators? I know you've heard of that. That's what particle accelerators are looking at. They're looking at matter and what's at the essence of matter. See, we've been able to divide things down to fine points. The atomic theory in the history of mankind is actually hadn't been around that long. We haven't known about atoms and molecules for all that long when you look at the history of mankind. But it seems like every time we get to the bottom level, there's still one more particle that's even smaller. The atom's not the smallest particle, okay? The neutrons are not the smallest particle. Protons are not the smallest particle. You can go down and down and down to bosons and other things, muons and all that, and they're still trying to find the essence of it, and that's what particle accelerators are all about. But they don't have one fast enough to do this. Can string theory possibly be an explanation for everything, a unifying theory? It may be, Who knows? But we certainly don't know that now. But they've been trying to find this unifying theory. Maybe we never will find the unifying theory. So what's the conclusion of all this? The conclusion for me is God, who transcends time, has created time, space, and matter in the beginning. All physical laws were created at the same time, and the current scientific thought relies on the two pillars, quantum mechanics, general relativity. But both have tremendous experimental support, and we don't need to be afraid of them. Okay, so the world works that way. God created the heavens and the earth. That's a broad statement, but he created them with mechanisms. There's nothing wrong with looking at those mechanisms, any more so than is looking at how disease occurs and how our body occurs. I don't see any problem with that, as long as we understand that there's a cause. Just like Hawking said, there's a cause and effect. When we look at our world and our universe, there's always a cause and effect. And the cause for these laws, and physicists cannot tell you why these laws are there. Can't begin to tell you the why. They can tell you they are. You know, they can say the speed of light is what it is, and they can tell you gravity is what it is, but they can't tell you why. And it need not make us suspicious of looking at science. So let's also keep in mind, though, no matter how smart, and Richard Feynman has a brilliant physicist who's kind of at the bedrock of quantum mechanics. He was around during the Manhattan Project, very beginning when Oppenheimer and that group met at Los Alamos, New Mexico, to invent the atomic bomb. Richard Feynman was there, and most physicists, that theoretical physicists, understand this. This is the way our world seems to work as we understand it now. We may understand it differently 100 years from now. But it does seem that these things work. But we would expect scientists at some day to replace these theories with different ones, and probably will, or at least modify them. And the thing is, though, any new theory, any new ideas, in my opinion, need to be interpreted in view of the Bible, and that is God created.